Hello. So this is lecture 25 in section 5. The second half of unsupervised clustering we will cover, which is on the partitional type clustering algorithm. So this is module 1, and we will focus on introducing the basic algorithm of K-means. Okay, just a little bit again background. This is the last part of the class, supervised model, and then a little bit of RL. And we focus on tabular data. So essentially, the given data are just the matrix form, and there's only the per column are the features, and per row are the samples. And also, we don't have those Y columns that are the given labels. So there are no label columns in the given data. So we just try to learn patterns, in this case, groups from data. All right, so we defined what is clustering in the last lecture 24, and we introduced the basics there, and also a basic algorithm, hierarchical clustering algorithm. And in this lecture, we focus on partitional algorithm. More specifically is the K-means, and also we put some of the advanced version is the Gaussian mixture model in the extra content slide. All right, so let's get started.
All right, so again, we're doing, there's no labels, and we're just handling this matrix data with only just the samples, column as the features, and row as the different inputs. The task here is trying to figure out the patterns, right? A very classic pattern in when you have no labels to predict. So in the end, if you think about labels, it's some kind of guidance, right? It's guided me to look for patterns. In the unsupervised case, there's no label, and you just have to assume something. There has to be assumption, a lot of assumption you have to make to perform unsupervised models. And then the most classic we covered the last section is clustering, and this is the simplest task is to group. So it's related to how humans think about organize the knowledge, organize the world, right? We perform, we chunk, we group things into chunks, and to make it much easier to manage, much easier to memorize. This is really related to how humans think about or manage the knowledge. So that's why grouping or clustering is a very, very basic task, because it's kind of a basic task how humans perform. All right, so we covered definition of what do we even mean group, what do we even mean similarity and distance and representation of objects, and also we covered hierarchical clustering. The most classic is the bottom up. They're a single link, complete link, or average link way to measure the distance among the clusters. And the drawback of hierarchical algorithm, which we covered in last class, was this is a very intuitive method. It gives you binary trees, a kind of binary tree type of organizing groups to organize all of the objects in your current data. But there's issue here is it's a very costly method. So if you do a naive hierarchical bottom-up clustering, it's n-cube cost. So then it's also like it's sometimes most cases generate more than enough because maybe what I really care is only groups. I don't even need this levels of groupings. I mean, that's just not necessary at all. So rather than having such a complete coverage of how you group the objects, let's just partition, just got bigger groups. And this is a much more computationally, much less costly task. So in the partition type of algorithms, and the most classic is K-means. And the extension of K-means is the mixture model-based clustering. And it normally all follows the same protocol. So you normally start from a random partition, and then you just refine it iteratively. So, so there's one important hyperparameters we have to specify about in the partition type of method is the number of clusters. And this is a very important hyperparameter, and it's very critical to get the right k, in this case, k number of groups. I'm trying to figure out how to group my object, group my samples, or group my inputs into k groups. And how do you even know k? But this k needs to be provided beforehand for a partition method to function. All right, so let's just, again, standardize the notation. So we have n inputs. I want to group it into k clusters, and each input is described by p features. And the reason why I try to standardize the notation is just to compare with hierarchical clustering later, and to see if this is indeed computationally more efficient and less costly. So P, so each object is represented by RP, for example, and then there are total n inputs. And you want to group them into k groups or k clusters. All right, so very simple, like if you are given this type of maybe nodes, they're geometrically represented in this two-dimensional space. Very, very naturally, you can group them into 3 clusters just based on density. So this is one way. The other, like this, while you're given this type of data, for example, this is age versus salary or age versus the assets. And then normally when you have more older, you got more money, but there's some kind of like not in a cluster point, like a lot of people very old, but they don't have money, or there's a group of people has very young, but they have a lot of money and inherited. So those naturally makes this into 3 groups. So so that's just how partition cluster work. So, and based on this, you can actually tell, I mean, there's something very important in this kind of cluster first is we normally have this kind of oval shape. We assume this oval shape. What do oval shape even mean? In fact, this is just a Gaussian distribution. You're assuming a Gaussian distribution in this cluster. And we actually revealed what do we even mean Gaussian distribution, right? Whatever this Gaussian distribution, what you care is the center and the covariance shape. So after we talk about k-means, and then the Gaussian mixture model, this is a very classic Gaussian mixture model based clustering. Sorry. What you care is, so sorry. Yeah, so what you care is the center. It's mu sub k, k from 1 to capital large K, and then sigma k, which is the covariance, measure the shape. And then also there's another is, what's the proportion of each of the cluster? And this is the biggest cluster, this is the second biggest cluster, and this is the smallest cluster. And this is also some information about cluster. This will get clear in the future slides, but let's start from the simplest clustering, partition clustering ever, which doesn't even consider the covariance at all. It only considers the center. So that's called k-means clustering. The k-means clustering is like the simplest partition method ever. So in the end, I'm trying to group my objects into k groups. And so how could you get the best partition ever? So there's one way we talk about in the hierarchical clustering, we can just enumerate all the possible clusters. and then we compare. So which of the clustering give us the minimal within cluster similarity, and then maximize the between cluster similarity. And you can just enumerate all the possible clusters. And however, but that approach requires to enumerate how many kinds, because for each data point, you have the choices to be in the cluster 1, 2, until k. So for every data point, we already standardized notation, right? You have total n objects. How many possible partitions? When you have n objects, partition into k groups. Very easy. K power to the n. And this is exponential, and this is just too costly because n is normally larger than 100, right? Even 2 to the 100 is a very, very, very big number. So let's just roughly count. 2 to the 100 means I'm trying to group 100 objects into 2 groups. And this is already a very, very costly if you do total brute force enumeration. So, and then people converted it into a heuristic-driven method called K-means. So there's actually a reason why performing K-means, but let's just for now think about its greedy method, heuristic-driven greedy method, because enumeration is just too costly. Yeah. So the K-means method is, so the user pick a K and randomly pick K points as the center point to start. And then decide all of the n objects, all of the n inputs, which one of the center from that K cluster you just randomly chose, each the closest. Then you think this point belongs to that closest center. After you assign every point into one of the K clusters, and you recalculate the center just using a min operation, and then this gives you a new set of center. Then you redo for each point, you try to figure out who is the closest center. And you just do it iteratively again. If none of the objects change the membership in the last iteration, then you actually just, this K-means stops. So this just like a pseudocode, let's just see the careful example run. Okay, so I have all those blue inputs in this two-dimensional space, and I want to group them into 3 clusters. Why 3? I picked 3. For now, there's no reason. I picked the 3. I want to group the points into 3 groups, and I don't know where are the 3 groups. I just randomly put those 3 centers to 3 random positions. So now, I need to decide each point, are they belongs to the first group, second group, or the third group. And very easy, I just use distance to measure. So is this center more close to me, or this center, sorry, it should be a straight line, or that center close to me. And very simple, and whoever is the closest, I belongs to that cluster. So for this one, it's super easy, right? So it should be K1. Now let's see, K2, this is the other points. Measure K1, K2, K3. Looks like this point belongs to K1 too. But it's, in fact, I mean, we know to be to know how the points in the space, in the two-dimensional space, belongs to a cluster. There's an easier solution is we just connect this K1 and K3, the line perpendicular to the connecting line, and also past the center of that line, separate the space. It separates the space into, maybe slightly. So, it's just basic geometry, right? Whoever on the upper is more close to K1, whoever is lower is more close to K3. And then you can just do this for every pair. K1 versus K2, separate the space it's very easy. I mean, through this middle line, perpendicular, I think it's right, but not entirely. Yeah. And then K3 and K2 with the same separation. Then, in fact, if you look at this, the three lines, there's a little bit, not entirely good, that's roughly. The three centers actually separate the space into mutually exclusive sections. And if you learned it in the algorithm class, this is called a Voronoi diagram, right? Just mutually exclusive partition of the space. So each set of K centers provide one Voronoi partition. Okay, so now I know this partition. I'm using this in the points within my current cluster to recalculate who is my mean. And very clearly, this K1 should be shifted to be more close to the right, right? Because most of the points are more close to here. The center, of course, should be more close to the right. And the K3 should be a little bit moved up because there are more points on the upper right. And this K2 very clearly should be more on the right, left. So that's how you recalculate the mean, and then you get the second round of the new center. Okay, so after you get new center, then you need to repeat the whole process. I need to decide, is this point, especially this point, is this point belongs to the K1 or K3? So actually you can tell because K3 got moved to here, and this point, even though it was belonging to the K1, now it clearly should now belongs to K3. So because of this is an iterative process, you are reassigning the membership, and after the membership got decided, you recalculate the mean. And then you need to do this iteratively again. Okay, question about this? It's a very simple method. Yeah, so, and then you do it, and then this point is shifted to, and then the second round, this got blue and more. So every time you have to decide for each xi, this is the first step. For each xi, which is my center? Is it K1 until K3? And you need to perform this distance measure calculations, right? Center versus a point, and there are total K points to decide. So we're going to do this later, and then you do an arg-mean of the current points versus all the centers, and then use the best as my current center. That's the first step. So all right. And then the second step is to recalculate the center, which is actually here. The second step is to recalculate the center. I should swap the two pages. So membership assignment and the center calculation. The center calculation is, you can tell it's it depends on how many points are here, and you perform a summation operation, and then you divide it, normalize it by the size of the cluster. Roughly, so the cost of this is, so what's the cost of calculating a mean operation? So, of course, this depends on the size of the cluster. And then you just perform a summation and then scalar division. But if you consider every point, so in the end, you need to perform a summation of endpoints, right? Total endpoints, sum, but even though they are not summed into one cluster, they're actually summed into k different clusters, but the number of summation operations are On. And because each of the xi is a p-dimensional feature vector, this step's cost is, I think it's ONP. Question about this? Yeah, it's a very, very simple operation, right? Sum, just summation, and there are p elements to sum. Yeah, it's ONP. All right, and then let's see this operation. Assigning the clusters, what's the cost? So for each of the sample, for every I, and there are a total of n objects, right? For each object, you need to calculate the distance of that object versus the k clusters. And each one of those, it just, let's assume that's Euclidean distance. Each Euclidean distance calculation is OP because there are total n p elements. So kj versus xi, and then for each object you have OKP operation, right? So this is OKP for each, and then you need to perform this assignment, membership assignment for all the objects, which makes the total computation is comments or concerns about this? Yeah, because for each object, you need to perform this distance calculation versus all the k clusters. That makes OKP. And then this is only for one object, right? You need to perform this operation for every object. There are a total of n objects, so that's why this is ONKP cost. All right. Okay, so again, so this is the Voronoi diagram. It's for each set of k centers, when the fixed centers, the partition the whole space into k mutually exclusive subspace to form a partition. And then this is known as Voronoi diagram, and then you change the position, and changing the position of k center leads to a new partition. So let's actually perform this even more because this is such a simple method. I want you to do it again. So, okay, so we start, for this case, I mean, actually to be honest, we don't know it's k to 5, but just visually use your eyes. Oh wow, 5 makes sense, right? You pick 5 centers, but the starting of the key 5 centers are very badly positioned. And you randomly guess the key center positions. Those are the red points. I hope you can read the red point positions. And then you just assign, there are actually much more points now. They're pretty densely located. And then using that k different centers, you can partition the whole space into this. And then you recalculate into each partition the new center. Very clearly, this center will move up, and this center may be a little bit up, and this center will be a little bit left. And then, yeah, so that's the second round of center. Then you're reassigning the, you jump to the new center, then you're reassigning and to get a new partition again, and many times until this reach its final convergence stage. And hopefully it reaches the convergence state. And actually it will. It always will converge. A very good property of K-means is the convergence is guaranteed.
Great. So this is the end of this module. See you in next module.